Okay.
Hello everyone and welcome to this webinar organized by Gonit Sora. Today we have with us Professor Amritanshu Prasad from the Institute of Mathematical Sciences, Chennai. Before going into the talk, let me mention a few things. Please use the chat option to ask questions. I'll put those questions to the speaker after the talk is over or during the talk if I see fit. In case your connection is lost in between, you can watch the Facebook live stream. I'll share the link in the chat in some time. And there will be a link with the feedback form provided during the Q&A session towards the end of the session. So let me introduce the speaker for today. We have with us Professor Amritanshu Prasad, who is a professor of mathematics at the Institute of Mathematical Sciences, IMSc, Chennai. He received his BStat honors from the Indian Statistical Institute, Kolkata in 1995. He then obtained an MS in mathematics in 96 from the University of Chicago, where he also got his PhD in 2001. Before joining IMSc, Professor Prasad was a postdoctoral fellow at the University of Montreal from 2001 to 2003. He has also held various visiting positions in India and abroad, including the University of Stuttgart, Australian National University, Institut de Etudes Scientifiques, I'm pronouncing that correct, TIFR Mumbai, Max Planck Institute for Mathematics in Bonn. He has received several awards and recognitions, which include the Young Scientist Medal from the Indian National Science Academy in 2010. He was elected Fellow of the Indian Academy of Sciences in 2019. He works in combinatorics and representation theory. He has several publications, including the book Representation Theory, A Combinatorial Viewpoint, which was published by Cambridge University Press. He's also interested in higher education and mathematics, mathematics popularization, and is a contributor to the open source software SAGE. Today, he's going to talk about cycles of a random permutation. Over to you, Professor Prasad.
Thank you, Vishal, and thank you, Manjul, for inviting me to speak at Gonit Sora. I've been seeing a lot of the good work that Gonit Sora has been doing in popularizing mathematics and helping students to giving them a lot of resources, organizing these talks, blogs, and so on. It's really a great pleasure and honor to be here speaking. And so I'm going to talk about something that's okay. So I'm going to talk about the cycles in a random permutation. So it's something that is related to combinatorics of the symmetric group. Some results that I came across during my research, they are not new. What I'm going to talk about, but uh, I just found them very interesting, and I thought I will try to share them with you. So I'll start with a little bit of probability theory. And what we are interested in, the main thing in probability theory that we're interested in is the Poisson distribution. So there are a few very natural probability distributions like the normal distribution or the Gaussian distribution, the binomial distribution, and perhaps the Poisson distribution. These are very ubiquitous in nature. And the way the Poisson distribution occurs is as follows. So you consider a sequence of random events. So you have a sequence of random events, and it satisfies certain properties. So to keep in mind the kind of random events we're looking at, one would be a radioactive disintegration. So you have some sort of unstable uh, isotope of some atom like uranium-238 or radium, and these atoms will at random times they will disintegrate. And if you're looking at radium, then the decay is very slow, and so for a short period of time at least, we will have that the conditions of the experiment do not change. It seems my video is frozen, so I'm just going to try to fix that. I'll just hold a second. Um, I'm not sure why this has happened. Um, so I'll just rejoin this. Maybe that will fix it. It's really gone, right? Let me just. Yeah, so the Zoom seems to have frozen here.
But we can still see your screen.
Okay, one sec. Okay, but Zoom has a pause. I was talking about the Poisson distribution, and we're talking about a sequence of random events occurring in time. So I was talking about an event like radioactive disintegration, where you have a certain mass of radioactive isotope and it's gradually decaying. And the total amount of stuff doesn't really change very fast. So at least on short time scales, the conditions of the experiment remain constant. Another example could be the number of phone calls coming into a call center, or you could look at the number of customers shopping at an e-commerce portal. So the assumptions are so it's a sequence of random events occurring in time. And the conditions are that one, conditions remain invariant with time. They don't change. So for all the examples I mentioned, that's true on small time scales. And the other condition is that non-overlapping time intervals are stochastically independent. That means that if you know some information about what happened in one time interval, it will have no bearing on what is going to happen in a time interval that is disjoint from that. And then we also have a certain rate. So I'll call lambda the rate of events per unit time. So this could be the number of atoms that decay per second, or it could be the number of incoming calls per minute, or the number of customers at the e-commerce website making purchases per minute, or something like that. So with these assumptions, um, you will get what is called a Poisson distribution. Let me derive for you heuristically the density, the probability distribution for Poisson based on these axioms. So what I'll do is I'll use a sort of discrete to yeah, I'll use a kind of discrete approach because this is mathematically somehow simpler. We don't need to talk about continuous probabilities. So we have this, let's see. So we have this time interval. Let's just draw it like this. So we have 0 to 1 time unit, and we'll divide it into small pieces. Each piece of length 1 over n. So we'll divide it into n pieces, each of length 1 over n. And if these, if n is sufficiently large, then it will be very unlikely that more than one event will occur inside each of these small pieces, right? So, so the probability of an event occurring inside in one segment is lambda by p, no, lambda by n. because we're expecting n events, lambda events to occur during this whole thing. So we would expect about lambda by n events. And at least for n large, we don't expect more than one event to occur in each of these segments. And we are assuming that the occurrence of events in these segments are independent. So if an event occurs in one of these segments, it has no bearing on whether or not an event occurs in another segment. So we can model this on a binomial distribution. So we can assume that in each of these segments, an event occurs with probability lambda over n, right? So probability that k events occur. And this is with this model where we're dividing it to n parts is binomial. So it's n choose k, and then the probability of an event in each this thing lambda by p to the power k, and then 1 minus lambda by p to the power n minus k, right? And now you take the limit as n goes to infinity. And this is not difficult. This is n choose k, which is basically n into n minus 1 and so on, following factorial of k terms. And whoops, this is lambda by n, not lambda by p. Yeah, and that will basically cancel with this n to the power k, because n minus I to the power n minus I over n to the power k goes to 1. So all those will cancel, and this first term will basically give us lambda to the k by k factorial. And the second term is one of the standard limits that you study in college. It is e to the minus lambda. So the probability of k events is lambda to the k over k factorial e to the minus lambda. And this is what is called the Poisson distribution at k. So definition, the Poisson distribution with rate lambda with rate or expectation. It's also turns out that lambda is the expectation of this. Lambda is given by probability of x equals k. So x is a random variable. The Poisson distribution is lambda to the k by k factorial e to the minus lambda. You can easily check that these things add up to 1, because if you take summation k goes from 0 to infinity lambda to the k by k factorial, it will just give you e to the power lambda. And so when you multiply it by e to the minus lambda, it will cancel out and you will get 1. So this is the probability distribution, and it arises, as I said, when you have you have this sequence of random events occurring in time, which do not change. The nature of the events does not change with time, and non-overlapping intervals are independent. Those are the only two axioms you need, and then you end up with this. This is one of the reasons why it's so ubiquitous. Okay, so that's the Poisson distribution. Okay, now maybe I'll just do a little calculation here. So so when you have a random variable, you can talk about its expectation. So expectation of a random variable, say any random variable y is going to be sum over whatever the values this random variable takes. In this talk, I'll be talking about random variables which take non-negative integer values. So k times probability y equals k. So that's the definition of the expectation of the random variable. It's the expected value that if you keep running this experiment many times, on an average, you will get this value. So let's just do some computations of for this random variable. So I will use the notation x subscript r to denote x into x minus 1 dot dot x minus r plus 1. So this is what's called a falling factorial. These are If x were an integer, this would be r consecutive integers decreasing starting from x. But x need not be an integer. X could even just be a variable, or it could be a real number. It's just a formal symbol. Then it's a polynomial in the symbol x. And let's just do a computation of the expectation of x r for the Poisson distribution with rate lambda. So this will be some k goes from 0 to infinity, and then we will have x minus 1. Maybe I should, now this will be k. Sorry, this is not k, this is y of k. The value of the random variable at when k is realized in the experiment. So this is so here I will get k into k minus 1 into k minus r plus 1 into probability of the random variable being k, which is lambda raised to k by k factorial, and then e to the minus lambda. But now these terms in the numerator will all cancel out, and this will become some k goes from r to infinity, 1 over lambda raised to k, and then we have k minus r factorial e to the minus lambda, which I can write as lambda to the power r summation k goes from 0 to infinity lambda raised to k by k factorial e to the minus lambda. And this last bit is equal to 1. So this is just lambda to the power r. So if you have a Poisson random variable, then the expectation of x into x minus 1 into x minus r plus 1 is just lambda to the power r. And using this, you can compute the the rth moment of this random variable, namely the expectation of x to the power r. You just compute the expectation of x squared x cubed up to x power r minus 1, and then you expand this thing out and calculate. Okay, so that's a little bit about the Poisson distribution. Now let me talk a little bit about permutations. So I will use the notation n. Okay, any questions up to this point? Maybe if there are any questions, Vishal can alert me.
None so far, but I will let you know.
Okay. I hope this is making sense.
Yes.
Okay. So I'll use the notation n to denote the set of integers from 1 to n. I'll use box n. And a permutation on n letters is a bijection from n to n. So I'll write Sn for this set of w function from n to n such that w is a bijection. And so this set has n factorial elements, and we'll use the one line notation for permutations. So I will write w as notation for this will be w1 w. Let me just say I don't know. So this is the notation w1 w2 wn. So for example, if I have 5 1 7 4 2 3 6, this is the permutation which takes 1 to 5, w2 goes to 1, w3 goes to 7, w4 goes to 4, and so on. Okay, so that's a permutation. And since these are functions, you can compose them, and under composition this set forms what is known as a group. So that means that this composition product is associative. It has an identity element, and every element has an inverse. So so this is actually a group with n factorial elements. Okay, So now I have this thing. I'll try to visualize this permutation 5174236. So I'll write down these numbers 1, 2, 3, 4, 5, 6, 7 in a circle, and I'll draw arrows to indicate where each number goes. So as per this, 1 goes to 5, 2 goes to 1, 3 goes to 7, 4 goes to 4, 5 goes to 2, um, 6 goes to 3, and 7 goes to 6. So this permutation now becomes a directed graph where the edges are directed arrows are taking each element to its image under the permutation. And this somehow very quickly gives us a bird's eye view of what this permutation is doing. Um, now each vertex here has to have one in edge and one out edge, because this thing is a bijection. So everything is the image of a unique element, and every element maps to a unique element. So this has to be a union of cycles. It has this directed graph has to be a union of cycles. This thing, for example, I can separate the cycles and show you. So there's a cycle which involves 3 goes to 7 goes to 6, and there's another cycle which involves 1 goes to 5 goes to 2, and there's the third cycle which only involves 4. So 3 goes to 7 goes to 6, 1 goes to 5 goes to 2, and 4 goes to itself. So this graph has 2 3 cycles and 1 1 cycle. And these are the cycles that I'm talking about in the title of this talk. So if you have a permutation, it breaks up into a union of cycles, and the cycle type. So if I call this guy W, then cycle type is an expression of the form 1 raised to A1, 2 raised to A2. I'm just writing it in this way, where AI is the number of cycles of size I, or I cycles. So in this example, the cycle type is 1 raised to, there's one cycle. There are no 2 cycles. So 2 raised to 0, and there are 2 3 cycles. And there are no 4 cycles. I could write 4 raised to 0, 5 raised to 0, and so on, but I won't really bother. I'll stop after there are no more cycles larger than that number. So that's the cycle type. And here's a basic question. How many elements W in Sn have cycle type 1 raised to A1? I'll use this notation alpha for 1 raised to A1, 2 raised to A2, etc. And note one more thing here, that so I'll call this alpha. The n, which I'll denote as absolute value of alpha, it's the size of alpha, is going to be A1 plus 2A2 plus 3A3 plus so on, because an I cycle contributes I towards n. So these cycles contribute 3 each, and this contributes 1. So 1 plus 2 into 3 is 7, which is the number of elements being permuted. Okay, so that's the question. And so really what we're asking is, how many graphs, how many directed graphs, which are unions of cycles, or maybe I should just say which are of cycle type alpha, are there. So basically what we are saying is we are putting the numbers 1 to n, and we want to somehow arrange these in the form of a directed graph where the cycles have type alpha. So the most, so suppose we are working with alpha equals 1 raised to 1, 2 raised to 0, 3 raised to 2 as in the previous example, then we can try to enumerate all the graphs with this cycle type. And there's one very obvious one. You just start with 1, 2, 3, 4, 5, 6, and 7. And that's, 1 goes to 2, goes to 3, 4 goes to 5, goes to 6, goes to 4, and 7. So this is sort of the first one that you would feel tempted to write down with cycle type alpha. And then you can get all the others by taking this and applying permutation to the nodes 1, 2, 3, 4, 5, 6, and 7. So you could replace these by, so this previous example I had 3, 6, 7, 3, 7, 6, 3, 7, 6, and what was the other one I had? 1, 5, 2, 1, 5, 2, and 4. And so this would be obtained, this second one would be obtained by the first one by applying the permutation. 1 goes to 3, 2 goes to 7, 3 goes to 6, 4 goes to 1, 5 goes to 5, 6 goes to 2, and 7 goes to 4. So if I apply this permutation to the nodes of this cycle, then I'll get the second cycle here. But it's not true that every time you apply a permutation, you will get different. If you apply different permutations to 1, 2, 3, 4, 5, 6, 7, you will get different diagrams with that cycle structure. For example, if instead of taking 1 to 3, I took 1 to 7, and I took 2 to 6, and 3 to 3. This permutation, so that means I would just take 1 and replace it by 7, 2 and replace it by 6, and so it would still give me the same directed graph. It's just that, so this would also give me the same directed graph. And another thing I could do would be to take 1 to 1. I could take this piece over here to this piece, and this piece over here to this piece. So I could take 1 to 1, and 2 to 5, and 3 to 2. Then I could take 4 to 3, 5 to 7, and 6 to 6, and then 7 to 4. So this would also give me the same thing. It would just interchange these 3 cycles. So what I can do is either I can interchange the cycles of the same size, or I can rotate along any of the cycles by by certain turns, certain number of turns. So the total number of ways of doing this, that is from one permutation, the number of permutations which give rise to the same cycle will be actually just product over ai factorial, which indicates that I can permute the cycles of size I times I to the power ai, where ai is the size of the cycle. That's the number of rotations I can do for each cycle. And this is the number of cycles that give rise to the number of permutations give rise to the same cycle, to the same graph. So overall I have n factorial. So this number is usually denoted z alpha. So overall I have n factorial permutations, but z alpha of them give rise to the same digraph with cycle type alpha. So the total number of digraphs with cycle type alpha must be n factorial divided by z alpha. Which is equal to number of permutations with cycle type alpha. And so we get an old formula of Cauchy, which is that the probability that a permutation has cycle type alpha this is equal to the total number of permutations with cycle type alpha divided by n factorial. So it is just 1 over z alpha, which, let me just remind you, this is product over I, 1 over I raised to AI factorial. So this formula goes back to Cauchy. So this is the first sort of result on a random permutation. So we ask, what is the probability that a random permutation has A1 1 cycles, A2 2 cycles, A3 3 cycles, and so on. Then this is this, of course, provided that, so maybe I should write it like this. Alpha has size n. That is A1 plus 2A2 plus. This should be equal to n. If this is not n, then of course this probability would be 0, because you could never get a permutation with that cycle. Okay, so that's the first result. Okay, now let's think of, so what I want to do is, now I want to think of these the number of cycles of different lengths as random variables. So you take Sn and you say this set Sn has n factorial elements, and you're choosing one.
There's a question.
Yeah.
So does the cycle type have anything to do with partitions?
Yes, the cycle type is actually a partition. This is a way of writing a partition. It's a partition in which A1 occurs once, A2 occurs twice, A3, 1 occurs A1 times, 2 occurs A2 times, 3 occurs A3 times, and so on. Let me give you go back to this example. This is the partition 3, 3, 1. This thing, 3 occurs 2 times and 1 occurs once. So these are the same as partitions of n. It's just a different parameterization of partitions of n. I'm glad you asked that question. I should have probably mentioned it on my own accord, but anyway. So, yeah.
Okay, thank you.
Anything else?
Nothing so far.
Okay. So now we know, okay, so if I type xi to be the number of I cycles of a permutation, say xiw to be the number of I cycles of a permutation w, then since this w is sitting in a probability space where I'm choosing a permutation at random uniformly, this xi is a random variable. And what I'm going to do is I'm going to calculate various moments of these random variables. So, but before I go on, let me just restate what I said earlier. Probability that x1 equals a1, x2 equals a2, and I'll put an n here to say that we are working with Sn. Xn equals an is equal to product. There's actually two cases, I greater than or equal to 0. No, I greater than or equal to 1, then no 0 cycle. I mean, we don't count 0 cycles. There's no such thing as a 0 cycle. And then we have 1 over I raised to AI factorial. And if A1 plus 2A2 is equal to n, and it is 0 otherwise. So these probabilities are not independent. However, each of these factors looks very much like So this remember this lambda raised to k over k factorial. This is 1 over I raised to ai over ai factorial. So this looks very much like a Poisson probability that a Poisson random variable is equal to k. But then there is this annoying sort of constraint here. And so we'll see that as you take n to infinity, this goes away, and we can really pretend that these random variables are distributed independently with Poisson distributions. So yeah, maybe I'll leave this here. So yeah. Okay, so this condition is what is a bit annoying. So yeah. Another fact that I should mention is that since the probabilities add up to 1, what we have is this identity that 1 is equal to summation over all a1 plus 2a2 plus. Otherwise, I can just write yeah, this is equal to n 1 over z alpha. Maybe I can just write this as size of alpha is equal to n. So that means sum over all a1, a2, a3 such that a1 plus 2a2 plus 3a3 is equal to n. 1 over z alpha adds up to 1. These probabilities all add up to 1. So this is a useful identity which we will use later. So we're summing over in some sense all partitions of n, this statistic, and it goes to 1, adds up to 1. Okay. So for example, we can already see some nice things. What is the probability that x1 equals 0, x2 equals 0, xn minus 1 equals 0, and xn equals, and then xn has to be 1. So you just have one n cycle. So what is the probability that a randomly chosen permutation is just one n cycle? And the answer from this is, of course, 1 over n. What is the probability that x1 is equal to n and everything else is equal to 0? That is 1 over n factorial according to this formula. And this is not surprising because this just means that there are only one cycles in your permutation, which means that your permutation is the identity permutation. And let me do just one more example. Probability that x1 equals 1, x2 equals 0, and so on. And I won't write the ones which are 0, and xn minus 1 equals 1. So this would still add up to n. And this is going to be by this formula. Now you have two factors. One factor is just 1 and the other is 1 over n minus 1. The reason I'm putting this one out here is that this is actually the most probable cycle type. This probability is even larger than 1 over n. This 1 over n factorial is the least probable. This is the most probable. You can try to see these as exercises. Okay. So now let's talk about moments. So let's take another partition beta equals 1 raised to b1, 2 raised to b2, and so on. And I want to compute, so this beta can be a partition of some other integer m, which need not be equal to n. And I want to compute some moments. So I want to compute what is the expectation over the symmetric group. So if I, of x1 to the b1, x2 to the b2, and so on. So this means expectation over, when I take a random permutation in Sn, what is, so expectation over Sn of x1 to the b1. x2 to the b2 and so on. We'll take only a finite product here. After some point, these b's will all be 0. Now this is a bit harder to compute, but even for the Poisson distribution, we found that it's easy to compute the expectation of this kind of polynomial, and we didn't directly compute the expectation of x to the power r. So we will do a similar thing here, and I will define x choose beta. I will define it to be the product over I of xi choose bi. So this x1 choose b1. So what is xi choose bi? By definition, this is xi falling factorial bi divided by bi factorial, or more explicitly, it's xi minus 1, xi minus bi plus 1 divided by bi factorial. That's what so I'm taking a product of these things. And let's compute its expectation. So maybe a new page is called for this. So this calculation turns out to be not very hard. Expectation of x choose beta in Sn. So this is 1 over n factorial summation w belongs to Sn, and then I have xiw, and I'll take product I greater than or equal to 1, xiw choose bi. Okay, but instead of summing over elements of Sn, I'll sum over cycle types. So what I'll write is as sum over 1 over n factorial, then partitions alpha of n. So that means a1, a2, a3, such that a1 plus 2, a2 plus 3, a3, and so on is equal to n. And then I will write, so this is given by 1 to the a1, 2 to the a2. And then I will write the number of elements with that cycle type. So that's 1 over n factorial. And I can kick in this product over I already, but this product over I raised to ai factorial. And then I have ai choose bi, because for the elements with this cycle type, xiw is just ai. So I get ai factorial divided by bi factorial times ai minus bi factorial. And then some wonderful cancellations happen. And what I can do is I'll take out this, I'll take out product over I 1 over I raised to bi factorial as common. And then I will get here sum over. And here I can write this as, now note that this thing is 0 if ai is less than bi. So I'm only worried about cases where ai is greater than or equal to bi. And I'm talking about what is left. So I have 1 over I raised to ai minus bi, ai is greater than or equal to bi, yeah, ai minus bi, ai minus bi factorial. But this inner sum is, so this outer sum is just 1 over z beta. And this inner sum, well, it kind of depends if n is, let me just write it down. So it's so instead of ai and bi, let's let ci to be bi minus ai. So I get sum over ci. And what is the condition on ci? So the condition on ci is that c1 plus 2c2 plus dot 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 is equal to, now remember, a1 plus 2a2 plus, and this is equal to n, b1 plus 2b2 plus dot dot dot, this is equal to m. So this should be n minus m. And if n minus m is negative, then this is an empty sum. and then this is 1 over I raised to ci factorial. So this sum in here is certainly of this form. It's a sum of this form where I'm taking partitions of n minus m. So this is 1 over z beta summation size of gamma equals n minus m 1 over z gamma. So this is equal to 1 over z beta if size of if n is greater than or equal to size of beta and 0 otherwise. So that's the formula. And what you see is that
Amri, maybe it'll be helpful if you can recall the notation here.
which one?
So, for example, what do you mean by x choose beta?
Oh, x choose beta. Yeah. Let's see. Let's go back here. So x choose beta is the product of xi choose bi.
Right.
And xi choose bi is just this xi into xi minus 1 dot xi minus bi plus 1 divided by bi factorial.
And what are the xi's? Are they just free variables?
Xi is the number of I cycles.
I cycles in an element in Sn.
In Sn.
In Sn, right.
Yeah. So here this calculation is happening in Sn for the fixed n.
Okay.
So first we try to sum over all the elements of Sn, but then we realize we can just these xi's and all are invariant for all elements in the same with the same cycle type. These things are the same. So now we just sum over the cycle types, and those are indexed by alphas, the partitions of n written in this form a1 plus 2 a2 and so on. And then you write it down like that. And so you have to put in the number of elements with a given cycle type, which we had computed, n factorial over z alpha. And then this is just xi choose bi, but xi for all elements in that cycle type is ai, because we're talking about elements with cycle type alpha. So,
right.
So you get and then the rest is fairly straightforward cancellation and rearrangement. The only point here is that the clever trick is that you only need to worry about ai greater than or equal to bi, and these things become dependent on ai minus bi. So you call that ci, and then you really get a sum over partitions of n minus m. So this is the main calculation here.
So beta is fixed and has nothing to do with n.
Beta is fixed, yeah. So beta is fixed. It could be a partition of any integer m, which could be n, or it could be larger than n or smaller than n.
I see.
But what we find is that if n is less than beta, the size of beta, then this thing has expectation 0. Just because I guess at least one of those variables will have to be 0, in fact. At least one of the xi's will have to be 0 in that case. But if n is greater than or equal to beta, then we get 1 over z beta.
Right.
So the upshot is that the limit as n goes to 0, en x choose beta is equal to 1 over z beta. Okay, so this is true. This is an equality for n sufficiently large. Okay, now let's go back to our Poisson variables. So suppose y1, y2 up to some y capital N are independent Poisson variables. And yi is Poisson with parameter 1 over I. So that means yi has probability that yi is equal to k is e to the minus 1 over I 1 over I raised to k over k factor. Right, so this is a Poisson distribution with lambda equals 1 over I. Then what we know is that the expectation of y1 falling factorial r under this yi falling factorial r is going to be lambda to the power r, so it's going to be 1 over I to the power r. And so what we get is expectation of yi choose bi is 1 over I raised to bi factorial, because this is just this thing divided by bi. So so what we get is that expectation of y choose beta. So this is again the same notation I'm using. This is the product of yi choose beta I bi is the same as this limit 1 over z. So what we are seeing is that these random variables y1, y2, yn have the same moments as the limiting moments of the random variables that come from the cycle types of a random permutation. So what we have is that limit n tends to infinity, expectation n x choose beta is equal to expectation y choose beta. This implies that limit n tends to infinity, expectation of x1. So this now depends on an n which is kind of, yeah. So x1 raised to b1, x2 raised to b2, and so on is also equal to expectation of x1 raised to y1 raised to b1, y2 raised to b2. Because if you compute the expectation of x choose beta, you can also compute the expectation of any monomial in x. The point is that these polynomials form a basis for multivariate polynomials. Just like these falling factorials, x, so 1, x into x minus 1, x into x minus 1 into x minus 2, those form a basis for polynomials in one variable. These things in the multivariate setting, they form a basis for all polynomials in the variables x1, x2, x3. So for every beta anyway, there are only finitely many random variables involved. So this is the observation that all the moments of these number of cycles are the same in the limit as the Poisson moments. And now in statistics, there's this a trick called the method of moments. So it's an old result. You can find it in a paper of Haviland in 1936. The one variable case is very well known, but I had to look a bit to get the multivariate case. But statisticians know this. So the theorem says that if you have a sequence of random variables x1, xn is a sequence of random variables and is a sequence of vectors of random variables, right? So each of this is a vector of random variables. We have a sequence of these. So these are the random variables of 1 cycles, 2 cycles, and so on, coming from Sn. Each of them gives you a different random variable. And y1, y2, yn is is a set of random variables, is a vector of random variables such that limit n tends to infinity, expectation of x1 n to the b1, xn n to the bn is equal to expectation of y1 to the b1, yn to the bn for all b1, b2 greater than or equal to 0. In particular, that means that these limits, these expectations are all finite. And then there's one more condition, and the joint distribution of y1, yn is completely determined. So this is a kind of technical condition by these expectation of y1, b1, yn, bn. Then this sequence, this sequence of vector of random variables converges in probability to y1, y2, yn. Which means that for any set whose so in this case we're talking about discrete distribution. So if we take any set in R to the n, so these random variables take values in okay, let's just put it this way: you take any subset of points in the n tuples of natural numbers, then the probability of those points will converge to the probability for y. So all the probabilities will converge. And so what we are saying is that for very large n, if you look at the joint distribution of 1 cycles, 2 cycles, 3 cycles, and so on in a random permutation, they behave as if they were independent Poisson random variables, where the ith variable has expectation 1 over I. So that's the upshot. So you can get some very nice consequences of this. For example, you have limit as n tends to infinity. What is the probability that x1 equals 0? So what is the meaning of x1 equals 0? So the meaning of, well, let's say x1 equals 0. That means there are no 1 cycles, which means that your random variable has your permutation has no fixed points. So the probability that a permutation of a large set has no fixed points is just the probability that a Poisson random variable takes the value 0, which is just 1 over e. So this is the famous party problem. This is from the days when mathematicians wore hats. A large number of mathematicians, say 300 mathematicians, go to a conference, and at the entrance they check in their hats, and when they leave, their hats are handed back to them in randomly. And what is the probability that nobody gets his own hat back? And that is roughly 1 over e. But you also, that comes straight from this, because we know that these things have x1, x2, x3 are independent, and so we just have to worry about the distribution of x1, which is Poisson with expectation 1. What is the probability that xi is equal to 0? Well, this is just 1 over e raised to 1 over I. And what is the expected value of x1 plus x2 plus xn? And if you're working over n, this is the expected value of the number of cycles, total number of cycles, because nothing larger will occur. So this thing goes to 1 plus, it grows like 1 plus half plus 1/3 plus 1 over, which is approximately log n. So if you have a very large permutation of a very large set, on an average, the number of cycles it will have will be like log n. Okay, so that's so you get a lot of very nice consequences like this. I'll give you a reference. It's a very nice paper It's a little terse. I mean, I spent this entire talk sort of explaining just maybe the first couple of pages, but it's a very nice paper. It's in the Annals of Probability, 1992, and it's called Cycle Structure of a Random Permutation, which is, I think, also the title of this talk. So they do more. They study the convergence more closely. And this proof that I gave is more or less what they also outline in the first section. But it's very terse. If you're not a statistician, you might find it a little hard to follow. So that's basically what I've fleshed out in this talk. Okay, so it's an hour. I've been more than an hour, so maybe I should stop now. Let's see if there are, yeah.
Thank you for this wonderful talk. There are a few questions. So, so since we have a less number of participants, maybe I can ask some of them to unmute themselves and ask. So, Salil has this question. He asks, could we have other representations like graphs and partitions? Yeah, can you hear me now?
Yeah. Question has been just presented. The only thing is, could the other representations run in parallel? So people can choose whatever representation they are comfortable with.
Vishal, I think Professor Prasad is muted. So,
Oh. Amri, I think you're muted.
Yeah. So no, I didn't understand the question actually. I don't understand what Salil means by representation here.
Salil, can you expand on that?
Well, this is Salil. We used one notation about regarding the permutations.
Yeah, one line notation.
We used one particular notation regarding permutations. So could we have other permutations? Other representations.
Yeah,
like
so
the graph.
another one that is usually used is a cycle type, right? So if I go back here, where is it?
So it's not really a question. It was just a comment.
Yeah. So here, for example, we also sometimes write this as 376 152 4. This is the cycle decomposition representation. This is the one line representation.
So I think what he means is just like you've taken the permutation and written it as a graph, and then you look at the different connected as a directed graph, and then you look at the different connected components, where each of them is a directed cycle. Are there other such ways of denoting a permutation? Am I correct, Salil? That is.
Yeah. Right.
Yeah.
Another very useful way is to write it in the 2-row diagram. No, 1, 2, 3, 4, 5, 6, 7. This is something I use. And then you say what goes where. 1 goes to 5, 2 goes to 1, 3 goes to 7, 4 goes to 4, like that. So that's another way to write it. I don't know what else. There's a matrix presentation. You can write a permutation as a permutation matrix. That's also very nice. It gives a visual two-dimensional feeling for it.
To get an certificate.
Sorry, did you say something?
I think I did not. Maybe someone else did. It's
Okay.
not clear. Okay, so I also have a few questions from my side. So
Yeah.
so you have this result where you have z beta as the denominator, right?
Yeah.
And that sort of seems like something related to where you could take perhaps permutations with beta as the cycle type. However, I mean beta size of beta might be different from n. Is there a combinatorial
Right.
way to see this?
I don't know.
I mean, perhaps one could think of it as just taking the first m elements and writing it out and leaving the others fixed.
So, yeah. So you would. Mhm. So you're saying there should be a bijective proof of this identity, perhaps?
Yeah, I mean, yeah, I
Maybe it should be something factorial over beta, m factorial over beta,
yeah,
of z
yeah.
beta. So then you would say that something is, yeah, I never thought about that. So yeah, so then that would be the number of elements with cycle type beta, and then you would be choosing. So the left hand side would be, yeah, that's an interesting question. It may be nice to find a bijective proof of this identity.
Also you mentioned about the party problem. So maybe if you can say something about that and
About the what?
the party problem,
Oh yeah,
problem.
the party problem. Yeah.
And maybe you can mention something about that and derangements.
Yeah,
Permutations.
so this x1 equal to 0, these are partitions, these are permutations with no fixed point. They're called derangements. What else should I mention? You can try to compute the number of derangements in Sn. So the standard way is to do it using sort of inclusion and exclusion. I forget, there's a nicer way to do it, right, Vishal?
Yeah, so it's like very good exercise in principle of inclusion exclusion, and you end up like if you take n tends to infinity, you get 1 over e, the probability.
Yeah. So you get a truncated expression for 1 over e, right?
Yeah.
So this is e inverse, and if you look at this, this is so it's 1 minus. How does it work? Minus 1 over. I forget now.
1 minus 1 over 1 factorial plus 1 over 2 factorial, minus 1 over 3 factorial, and so on.
And all these truncated series are positive, and they actually, if you truncate at level n, I believe it gives you the number of derangements. So,
Right.
so 1 minus 1 over n factorial plus 1 over 2 factorial minus. Is equal to probability in Sn, Pn of x1 equals. So this is the exact value. So that itself is not so hard to show. I wonder xi also may have a similar expression. I'm not sure now.
Oh.
So, but from this kind of Poisson thing, it all comes all very easily. So I don't know if x2 equals 0, for example, you can write down a similar expression.
Right.
Or x3 equals 0.
I think Manjil has a few questions as well. So maybe you can mention them.
So not from me actually. There was a question on Facebook, which I can say. So the question was, what is the complexity of the problem of factoring a permutation into cycles?
That shouldn't be hard, right? I mean, you just yeah, you should be able to do it in n steps. It should be linear. You just start somewhere and then you get till you come back. Once you come back, you have got a cycle. Then you take something which is not in that cycle, start somewhere else, and come back. That's very easy. So it should be linear in n. I would say, I would guess.
So you mentioned this result about Havil and
Yeah.
So can you go back to that?
Yeah, I noticed you put up the exact reference, in fact, which was right spot on. I think, yeah, this is an interesting subject, actually. Yeah.
So you did not prove this, right?
No, I didn't prove this.
So what is the special case of this which you proved?
No, I just used this. So what we see is that all the moments of the x1, x2, xn converge to the moments of independent Poissons.
Right.
So if you use this, it implies that the x1, x2, xn converge weakly to y1, y2, yn. So there's this little hypothesis here that the joint distribution is completely determined by the expectation. That's a part of what a very interesting theory called the moment problem. So firstly, the moment problem is you're given a bunch of numbers and the question is, can they be the moments of a random variable? So you have the one variable problem, is just given a sequence of numbers and you want to know, does there exist a random variable which has this sequence of numbers as its moment? And it's not always true. There are some conditions which I think Bishal may remember from Xavier's course. In the multivariate case, the problem is a little harder, but that's not concerning us here because we already know that this y1, y2, yn are moments of a Poisson distribution. Then there is another question about determinacy. Is there a unique probability distribution for which these are the moments? And so that's the second hypothesis over here in this problem. And that is there's a criterion due to maybe it's explained in this Aratia and Tavares paper, but there's a criterion due to what is it? It's the name. Let me try to recall the name. Yeah, maybe it's Karleman or Shuhat and Tamarkin, but let me just, so you'll find it in Aratia and Tavares paper. And the fact that this holds for Poisson distributions is found in the PhD thesis of Edwards, which is easily available online. It's, I think, a University of Michigan. Let me see if I can.
There's one last question, maybe. So this is again from Salil. So he mentions that we see a log n. So is there some connection to the Euler's constant?
I don't know. We see, in fact, the harmonic sum and log n, right?
Right.
No, I'm just saying that, if you have a very large permutation, you expect about log n. It's an asymptotic result. Maybe a closer analysis of things. I'm not sure.
Right. Yeah. So the tilde symbol is that it is an asymptotic result. It's not equal. It's
Yeah. It's distinct as O of 1.
Yeah.
Right.
So and yeah, and then finally, I'd like to ask if you can recommend some books related to this talk and how one might get into this subject.
So, random permutations, right? I actually have not really thought about random permutations. The reason I thought about this was that I was working on characters, and then these kind of sums come when you calculate the inner product of two characters. You need to average over the symmetric group, and that's how I came across this. And then when you asked me to give a talk, I thought, well, why not recast this in terms of random permutations and make it a little more accessible. So, but is there a authoritative reference on random permutation? So there's a very beautiful paper of Shep and Lloyd. That's really lovely. It's an old paper. It's maybe 19. It's rather old. I don't remember. Again, I'll have to. Yeah, I have it on my laptop. It's from 1966 in Transactions of the American Math Society.
In Lloyd Shapley value?
Sorry?
Are you talking about Shapley value?
Your voice is not very clear to me.
Okay. Is it better now?
Yeah.
Are you talking about Shapley value?
What value?
Shapley.
I think are you talking about Shapley value from game theory?
No, this is Shep.
Shapley value, yes, right.
Mm.
Yeah, I've written it down here. Ordered cycle lengths in random. It's in the Transactions of the AMS 1966. So this is a classic paper. Arvind Iyer told me that it's a very classic paper, well known. So, but he does a different kind of thing. It's also a very elegant method. Doesn't do this moment calculation. He as in they, I guess. Yeah.
So with that, I'd like to. I don't think there are any more questions, and with that, I would like to advertise that the next talk is on Sunday, which is where you can see more on probability theory by Professor B.V. Rao from Chennai Mathematical Institute. So it's at
Fantastic.
Sunday, 2:30 p.m. And again, I'd like to thank Professor Amritanshu Prasad for giving us his valuable time and for this wonderful presentation. Thank you. So
Thank you. It was my pleasure.
So the feedback form has been shared.